Let's look at work problems that involve springs. Uh, Hooke's law is the function we're going to use that tells us how much force is required. Hooke's law tells us that the force required to hold a spring stretched x units beyond its natural length is proportional to x. And the value k there, f of x equals kx, k is called a spring constant. Each individual spring has its own constant, and the units for it are newtons per meter. So let's look at a spring for a second. So I've got this little spring, and its natural length is whatever the length is from one end to the other. Now, if I just hold the spring like this, it doesn't take any force to hold it at this length. I mean, so if I do exert a force across it, the string's going to stretch. If I exert a certain amount of force and stretch it 1 centimeter, if I stretch it another centimeter, so 2 centimeters, it takes twice as much force. So that's the idea behind Hooke's law. You know, they even make scales that use a spring where sometimes it has a hook and you hang things on it, and however much it stretches the spring determines where the little needle on the scale points. So anyway, that's the idea behind this, and I think this only applies, at least we're only going to apply it to strings that you stretch, not compression springs. So let's look at this. Uh, Let's look at this first example. A spring has a constant of 5 newtons per meter and a natural length of 30 centimeters. How much force is required to stretch it from 35 centimeters to 42 centimeters? All right, I'm not going to get too tricky on you with these as far as throwing different units at you, but I might give you centimeters or millimeters, and the thing is you always have to convert these back to meters because of the whole thing about 1 joule is 1 newton times 1 meter. So if you're given centimeters or millimeters or anything, you got to convert it into meters. So let's look at this first one. The spring has a constant of 5 newtons per meter. So that tells us right there, k is 5. And so f of x is 5x. So that's the function that we're going to integrate. So the work done here is the integral of 5x dx. And we've got to put our endpoints on there. Notice what Hooke's law says. It says units beyond its natural length. So this spring, we're going from 35 centimeters. Well, the natural length is 30 centimeters. So when we start off, we're 5 centimeters. There's 5 centimeters of stretch. So we're going to go from 0.05, converting to meters, and then 42 centimeters, that's 12 centimeters above the natural length. We'll put that in as 0.12. And now this is a pretty easy integral to do. This gives me 5/2 x squared. Let me write that again more legibly. So you get 5/2 of 0.12 squared minus 5/2 of 0.05 squared. And I'm going to stick that into my trusty calculator. Let's see. Actually, when I put it in my calculator, I'm going to do one other thing. I'm going to do 5 over 2. I'm going to factor that 5/2 out so that I get this. And this is going to be a fairly small number. Let's see, 5/2 times parentheses 0.12 squared minus 0.05 squared. Yeah, that gives me, this calculator gives me fractions. It gives me 119 over 4,000. Let's convert that to decimals. 0.02975. And that's in joules. All right. By far the most common mistake I see people making on these problems is forgetting to translate these into either into meters or forgetting to subtract out the natural length of the spring. So let's do another problem. A spring has a constant of 3 newtons per meter and a natural length of 75 centimeters. How much work is required to stretch it from 1 meter to 2? All right, I'm going to jump straight to the integral here. We integrate 3x dx. And what are our endpoints going to be? Well, if the natural length is 75 centimeters, when we start off, that's stretched 25 centimeters. And then when it's stretched to 2 meters, that's 125 centimeters. So let's see, that's from 0.25 to 1.25. So let's see, what do we get here? 3/2 times 1.25 squared minus 0.25 squared. Again, I'm just going to stick that in my calculator. 3/2 times 1.25 squared minus 0.25 squared gives me 9/4. I'm going to write it as a decimal though, 2.25 joules. All right, let's look at the next one. This one's a little different because they don't tell us the spring constant. They say it takes 25 newtons to hold a spring stretched to 30 centimeters. Its natural length is 20 centimeters. How much work is needed to stretch it from 20 to 32? Okay, so first up, what we need to do is use this bit of information here to find the spring constant. Find K. Now, the thing to remember is F equals Kx for force. So with this, the force that we're dealing with is 25 newtons. K is what we're looking for. And that says stretched to 30 centimeters. So if its natural length is 20 centimeters, that means it's stretched 10 centimeters, which is 0.1 meters. So multiply both sides of that by 10, you get K is 250. All right, once we've done that, it's just a matter of setting up the integral. The work required is integral of 250 x dx. And let's see, its natural length is 20 centimeters, and we're going from 20 to 32. So 20 centimeters is 0 beyond its natural length, and 32 is 12 centimeters, or 0.12 meters. So if I integrate that, I get 250 over 2x squared, from 0 to 0.12. So that's 125 times 0.12 squared minus 0 squared. So again, 125 times 0.12 squared is 9/5, or 1.8. 1.8 joules. My example is missing here. Let's do this last example. A spring with a natural length of 50 centimeters is stretched to a length of 90. If the spring constant is 2 newtons per meter, how much energy is stored in the spring? This one is worded differently than the other problems, but it's asking the exact same thing. Because if you stretch the spring out, there's an amount of energy stored in it, and that amount of energy is the amount of work that you had to put into stretching it out. My cat over here is wanting some attention. You might hear him meow a few more times. Let's see. So let's see. The spring constant is 2 newtons per meter. So that's 2x dx. Its natural length is 50, but it's stretched to a length of 90. So that means that it went from its natural length up to 90 centimeters, which is 0.4 meters. So this is going to be x squared, 0 to 0.4. So that's just 0.4 squared, which is 0.16. Yeah, 0.16. So 0.16 joules. So how much energy is stored in it? Not a whole lot, 0.16 joules. All right, that's it for the spring problems.